And I'd like now to engage students. So not just faculty or people from the outside, but I'd like the students to start to engage in thinking about carbon capture, sequestration, and the energy of the future. It's your future. Students. You want to ask a question? Sure. Could you identify who you are and what school or whatever you do?
Hello, I'm Kaushik. I'm doing my master's degree in chemical engineering. I have a question for Ms. Sally. It was a wonderful presentation, ma'am. Thank you so much. It's like you told us about geological carbon sequestration, right? And I'm basically from India, so there is not much of scope in that. There was a mention of that too. And I recently went through an article where we do carbon sequestration by converting the carbon dioxide into baking soda. There is a suitable solvent which we use to convert carbon dioxide into baking soda, which probably might not be a geological sequestration process. Have you come across such kind of things? Because I don't know much about the solvent use because it is patented, and I've gone to the industry which does that. And do you have any idea about that, ma'am? That's the question.
Well, the two of you, I guess, can answer that, or all three.
Okay, so just so I understand, so you're saying that reacting CO2 with baking soda?
We use a solvent. They kind of use a solvent which they didn't tell me about that.
Okay.
To convert that into baking soda because instead of.
Oh, okay. So basically they're making a mineral. So it's a sort of basically mineral carbonation. I mean, it certainly is appealing as an option because it's a solid. The question is how much energy does it take to do that? And if you look at the reactants needed to produce that product, where is that coming from? What are the materials required? And historically, mineralization has been quite energy intensive if you try to accelerate the processes so that you can use them in industrial scale applications. Klaus may also want to comment because he did a lot of work early on mineral carbonation.
Yeah, the first point is exactly what you said. If you want to make a carbonate out of the CO2, carbon dioxide is an acid, then you need the base. So you need to find it somewhere. And it turns out that there's a significant energy cost in basically making the reaction happen. On the other hand, you could afford the mining. You can think of what's happening in Iceland as doing just that because you have a longer time. I'm sort of looking at it again, and I'm looking at what Greg Dippel is doing in British Columbia, who's looking at mine tailings and say, look, they carbonate spontaneously, and it's actually quite significant in total. So you could start saying this is a perfect place to start, because here something happens for free, and now if I invest a little bit, I might be able to push it further and harder. And so you could actually give me a price to start with and say, I can do as much effort as this price would allow and no more, and see how much I can do. So I see, when I started, I was looking at high energy intensive processes. The idea was I grind up the rock and I react it with CO2, and then I do mineral sequestration, and because it's a high temperature, high pressure process, I end up having about 30 minutes in which the reaction has to complete. Otherwise, I can't pay for the reactor vessel because it scales with the reaction time. And the other extreme is what I sort of would say, you take your lessons from heap leaching and you do a very slow cooking process where it's very mild and the conditions, and you move up. And I do think there's some potential there. Then the extreme of this is you go underground, marry it to geological sequestration, and say, if we come back in 50 years, so in the heap leaching I have months, right? Before I had 30 minutes, now I have months. And if I now go underground, I say if it's done in 50 years, and I can come back and monitor it in 50 years and say, look, it's all carbonate, we are done. That's actually a very interesting approach. So I see some future, but it is a slow process.
Yeah, and it definitely is a great topic for research.
So this is what we're talking about. We're talking about making this stuff, right?
Pretty much.
Ken, you want to say something?
There was an injection experiment recently in Iceland where they found that
we always thought it was decadal, centennial scale for the mineralization process to take place. It was subannual in the material. Geology is important, right? It depends on the material. So basalts and serpentinites apparently are sponges, and they will mineralize. The sandstones that I showed you and talked about, it probably is just like the slide Sally showed from the IPCC, where it's decadal, centennial scale before you start to get mineralization. But in Iceland, you can do it, and it turns into your chalk in a year.
Yeah, Dave Goldberg at Lamont has pointed out that if you look at sites which are already below the ocean, Iceland is sort of a point where the mid-ocean ridge came out of the water. You now have plenty of water. You have the high permeability you have in these rocks, and so you could do it in many places in relatively shallow water and play the game there. So you may have the capacity there.
And I think this highlights kind of a bigger point, and all the speakers talked about a need for a carbon price. And one of the questions is, among these various pathways, are we going to highlight ones where the entire cost of sequestering carbon would have to be borne by a carbon price, or are we going to highlight, as you're kind of suggesting, that there are some other pathways where there's a subsidy, 100% or less, that might come from the useful materials, which Klaus's quick 30-minute process seems much more viable than something that's decade scale, where you wouldn't be getting any payback on the products you would get out of it for a long time.
But just a slight caveat on that. So there's been a lot of interest in, reuse, making valuable products, and really the only thing that we use on the scale of our CO2 emissions are fuels, and all of the other materials are maybe equivalent to like half a gigaton of carbon dioxide. So they might be helpful in terms of a money-making prospect. On the other hand, they're probably not going to be available at the scale we need them.
But they may be important, not so much because they put a lot of CO2 away. I think that the bottom line is, in the US, we are good for about 16 tons of CO2 per person per year. Right? There's not terribly much we use, except for water, which we use on this scale. So you very rapidly run out of options unless it is fuel. But I could see that a lot of these new technologies start expensive and have to get cheap. And there, the fact that at the small scales you can actually make money on it might be the difference. It allows you to get started, but then you have to ultimately think of it as a waste management problem where you get a tipping fee for putting it away.
Okay. You have another question over here?
Okay, so my burning question was, speaking of half a gigaton, somebody said that was about how much biology could sequester. And I'm curious about that because I'm thinking, what about a massive get rid of the desertification, like combat that? Like what could we do a makeover? That's one. And then number two is, what about those bubbles of methane in the, isn't that going to be an order of magnitude more to deal with?
You mean like hydrates, methane leaking out? Is that
the bubbles in the permafrost?
Oh, right, yeah. So it's which is really huge. So the question is why couldn't we convert areas of land that are currently perhaps have very low biological productivity, to convert those to be forests or grasslands? So the question is do we, it needs other inputs, so it needs water, some things need fertilizer, so in some places that might make a lot of sense. What probably makes most sense is that we have many degraded lands that used to be much more biologically productive, and through poor agricultural practices, we've made them fairly infertile. It would be possible to try to restore those lands. That's particularly interesting because they may be in areas where there's adequate rainfall and so forth, if we could just help them, get reestablished. So that's a very interesting and important thing, because it also provides other co-benefits for providing habitat, other ecosystem services like watershed management. So those are quite appealing. In terms of the overall size of that potential, I don't know what the latest numbers are. Does anyone have a latest number on that?
Yeah, so this highlights something that came up very early on, for example, with this BECS technology, so biomass energy system with carbon capture, which don't have to be in the same location. So one version of this is that under either just the US decides to do it or under this Paris Climate Accord, we invest significantly where there is degraded lands. A significant amount of degraded lands in the Sahel in Africa, in Southeast Asia, and the growing potential in some of those areas is very high, right? It's not just temperature, but also water. And so if one was to be reinvesting in more sustainable forestry and better agricultural practices, there's an opportunity to use the climate crisis as a way to reinvest in things we should have already done, right? So that's kind of this interesting multi-win. In Southeast Asia, where there's been a huge amount of rainforest conversion, the Amazon, and largely in West Africa, the opportunities for this are very large. At the scale of communities and energy projects. In terms of the gigaton level of carbon sequestration, though, there's a real worry, are we going to really be able to do that at scale? And I think this is probably seen better as a way to reinvest in things we should have been doing than as our go-to way to sequester carbon.
Yeah, I think in the short term, we in a way, we have a crisis, right? So in the short term, this can help. But if you ask how much are you having standing, you said 800 gigatons. My number I usually use is 600 gigatons, but we won't quibble.
We won't quibble. 200 gigatons among friends.
Right, but the bottom line is that's the standing biomass. So you basically, on my scale, in 60 years, and his scale in 100 years, you are going to, actually even in US, because we are pushing 10 gigatons a year now. That's right. In carbon. So in less than a century, you have to double all the forests in the world. Put another way, we didn't create the problem by cutting down forests. We added to it, but we didn't create, the bulk of the problem is something else. So putting the forest back won't help. Another way I like to always put it, your metabolism is about 100 watt, right? That is being paid for by agriculture. Your industrial, commercial metabolism is 10 kilowatt. It's 100 times larger. And I have a very hard time seeing agriculture, which is good for the 100 watts, suddenly jumping in and taking care of the 10,000 watts. It's just, that I think is the fundamental challenge. And if you do back of the envelope, you end up saying the entire world is covered in forestry. You do more than current agriculture in order to balance the books. So but I have changed my mind on the standing biomass because I do see the overshoot scenario, and I think we should get away from saying we will peter out somewhere in asymptote, but we have to come back. And if we come back in 50 years, the lifetime of a tree is exactly that time. So if you cut it down now, you took a loan which you have to pay back right in the time when you go over the peak. And by the same token, if you grow a tree now, it will help you right as you go through this peak. And we need to start thinking about those things too.
Yeah, in other words, you critically buy time for these other technologies to come online if we had a much more sustainable land use policy. And we're leaving out the ocean, which of course is 3/4 of the planet, but we've talked about some of the complications there.
So you also had another question about, the potential release of methane into the atmosphere from melting tundra and so forth. And indeed, that's happening. It's documented. There are many scientific activities now in the Arctic, as an example, measuring, these releases. And it speaks really to we don't have a good technological fix for those problems. The best fix we have is to do everything we can to limit warming to the minimum amount possible. So, but it is definitely a concern.
We have another question over here.
I have a question for the two panelists from California. When I saw the bios, I said, I can't lose this opportunity. If you could explain what's going on with the Aliso Canyon electricity storage project, and perhaps a little bit of a timeline for the rest of the world to be able to look at the costs and the success or failure of what's going on. It's fascinating, and the information we're seeing here on the East Coast is very sketchy.
So the broader context is that as part of California's plan to hit its 2020 target, which is to be 33% of electricity from renewables being defined as solar, wind, biomass, geothermal, excluding large hydro, excluding nuclear, which is an add-on to that, and our 2030 target of 50%, is that California also passed a storage mandate. And the language of the storage mandate is that by 2020, we need to have 1.2 gigawatt of capacity. I'm not going to worry about total capacity versus kilowatt hours, but 1.2 gigawatts of peak capacity available in new storage. And California, on the hottest summer day when demand is at absolute peak, is about 60. So it is a couple percent. And the goal is to meet that with newly deployed storage technologies and then to up that number in a couple years after 2020 to perhaps be 3 or 4%. So building a storage industry which is acknowledged not likely to be cost competitive in the very near term, just the way solar was in the beginning. And so we're investing in a long-term option, and with the very low prices of natural gas today, you're sort of saying we only are doing this because we have a long-term strategy. So this is a very long hand-waving introduction to say what your question. It will be hard for you or anyone in California or outside to find the actual project cost of the Aliso Canyon storage or some of the flow battery storage technologies or others right off, because they are tied into using parts of California's cap and trade revenue to reinvest, to get private sector companies and utilities to invest in. Cutting all this away and off the record, which of course any meeting like this is off the record. Right, of course. Oh, you turned it away. Okay, that's great.
But it'll be on YouTube.
If you are a peak user of electricity, so you're an energy hog on the residential level, you're paying about 33 cents for your marginal cost of electricity, your most expensive kilowatt hours. Aliso Canyon and others will probably come in somewhere about double that. And that should not actually scare you. When Germany did its first feed-in tariff for electricity, the rate that was being paid out, admittedly unsustainably, was well over 60 US cents per kilowatt hour, but dropped very rapidly. And of course, there's a big debate about the German energy transition, the Angewende, but as other countries and as Germany figured out how to manage it better, that marginal cost penalty, if you will, has dropped and dropped and dropped. Some countries have done their feed-in tariffs well, others not so well. But the price numbers I highlighted in my talk, with solar at utility scale starting to come online at prices that no other technology can touch, highlight what we're banking on for storage. So that was designed to be a little bit of detail, but a bit of a hand-waving answer to the question.
Yeah, just to say a little bit more for context, so Aliso Canyon was the site of a natural gas storage facility that had a very, very dramatic leak that persisted over several months, and community had to be displaced. And so basically, and California is incredibly reliant on its natural gas generation to meet late afternoon energy demand. When the sun's going down, our peak is going up, and we literally are ramping. Today, we'll probably ramp 15 gigawatts of natural gas generation in the period of 2 or 3 hours. And so when in Southern California, when that gas supply was curtailed, they had to scramble to think about what would be a good option to try to help mitigate that risk. And I think it really remains to be seen how well we get through the summer, because the amount of ramping we're doing with natural gas generation is enormous today. And I will say, I think the California independent system operators do an absolutely fabulous job of managing something where no one's gone before.
And I guess let me just add one last piece of context to it, and that is that in the California context, the mandate for 2020 is 1 million solar rooftops. And 5 years ago, skepticism was high we would get close. Now California is over 600,000 solar rooftops, and almost everyone is confident we will be there or close to that. California then went ahead and said 1 million electric vehicles is our 2020 target. And we're about 300,000 today. So we are not as close, but we started much later, and the skepticism was even higher then. Electric vehicles are far from a perfect way to store energy we'd feed back into the grid because of round trip costs and things, but it is one of those levers that we're looking at this storage mandate and other feeding in. And so the long-term goal, not by 2020, but the longer-term goal is that with stationary and potentially mobile storage, we'd be able to beat down what Sally's talking about in terms of the so-called duck curve, this huge ramping demand that we would need, recognizing we don't have to solve that problem in the next few years. We're sort of thinking about a decade-long timetable so that that ramping goes down. And just like in Germany, California is forecasting already a huge over-generation of clean energy during the day, largely solar, and finding ways to soak it up usefully and then be able to re-inject some of it during these peak times.
So one of the reasons I'm interested in that part from the air capture perspective is I don't really want to think of it so much as a storage, but as a flexible consumer. In other words, if you want to make liquid fuels out of electricity, you cannot pay more than 2 cents a kilowatt hour, and I could probably make a coherent case that it's not more than 1.5. But if you push more and more renewable into the system, you actually could say part of the day you may get a good price because consumers are buying it, and other parts of the day, you, rather than curtailing, you are using it and you need electrolyzers or magnetrons to make microwaves, but you need some way of converting this electricity into splitting up either H2O into H2 or CO2 into CO. And I think there actually is a very interesting research issue right now because we do not have low-cost electrolyzers which can afford sitting idle. If you look at the Norwegian electrolyzers, they're about $2,000–3,000 a kilowatt. And if you are that expensive, you better run 24/7 in order to make up your capital cost. But in this world, you would probably run 10%, 30% of the time. And we need to learn how to make low-cost electrolyzers rather than ultra-efficient ones. And this is very hard to convince a chemical engineer to think about because they say, well, I can get the efficiency from 80 to 85%. I say, in the end, if it's 50%, it's good enough. But you need to get the capital costs down by an order of magnitude. But then again, looking at your mass production, I think this is perfectly feasible if we set our mind to it, but we need to do it.
Hi, my name is Jake. I'm an undergrad here. So California is generally seen as having pretty sound policies that have encouraged solar. But I've heard criticisms that sometimes that creates situations where companies are perhaps overly dependent on things like subsidies and rebates and stuff. So given that for other states trying to encourage like a nascent solar industry, what policies would you recommend that would at the same time subsidize them but avoid this like criticism that they're falsely dependent on subsidies?
Sure. You know, the ideal situation that would create a level playing field for all kinds of low carbon generation would be to have a carbon tax. And a carbon tax at $30 a ton or 40 or 50 would certainly be enough to incentivize things like solar energy and so forth. But it wouldn't pick winners and losers. But we're probably not going to have that. So I do think that the renewable portfolio standards have been very effective. The pioneers who sort of went first with those, you know, bore the brunt of the cost. So Germany, you know, we all really owe a debt of gratitude to Germany, who was willing to do their feed-in tariffs, which really drove the market, which, you know, led the Chinese to invest in all these plants. So anyway, I think that's a good option. You know, so California has had a real hodgepodge of a policy. One can think of like a policy quilt, you know. And so, for example, there's subsidization of rooftop solar. On the other hand, there's a renewable portfolio standard for utility scale renewables. And And I personally think that that made the landscape much more complex and created a situation where the suppliers are very, very reliant on subsidies. I mean, the reality is right now not a lot of people are making money on renewable energy. I mean, you look at all of the companies, you see lots of bankruptcies. And so I think we need to get to a stable price on carbon, with it gradually ramping up in a predictable but significant way, and let people really start working out, market-based economics.
And I guess the question is interesting because there's a whole bunch of features that tie into that story. So California's carbon price today, now our market's only 3 years old, so you can argue that it's young enough and it hasn't gone through sort of the not quite disastrous, but close to disastrous issues that plagued REGI and plagued the ETS in Europe. But in California, there's a price floor and there's a price ceiling. The price is tracked very predictably where we expected it to be. It's about $12 a US ton today. China's going to open their carbon market later this year, and China's five-province experiment had carbon prices anywhere from $5 to $20. So there's skepticism or optimism, depending who you are, whether China's going to get to do this nationwide and tie it all together. But these prices are not horrifically different than the number that Sally mentioned. In the scenarios I showed with Switch, $30 to $40 a ton in 2040 gets you there in many ways, not necessarily in industrial and chemical issues, but in a lot of this basic story. So the pathway to get there looks viable, but you have to stay on it. And price fluctuations in the carbon markets in Europe went from 4 to 35 euro. REGI, I think, is about $4 today. Of course, New Jersey's not a member right now. But there are policies that are seen as natural bridges. There's a lot of interest right now in California and elsewhere in so-called fee-baits, finding policies that penalize dirty processes, transfer the revenue from penalizing dirty to people or companies that buy clean products, whether they're vehicles or whether they're more efficient heat pumps and things, and to try to find market mechanisms we can use now to put on top, which makes Sally's story even trickier, right? It's even more of a hodgepodge. But the idea is we do these in the interim term until the carbon prices do get to the levels we're talking about. So it's a mix.
Yeah. Can I mean, there's a huge discussion about cap and trade versus carbon taxes. At Stanford, we've been working hard on a revenue neutral carbon tax. And what's meant by revenue neutral is that the taxes would be collected and they would be returned to the population. Every person would receive, their $300 a year carbon rebate. There is a program like this in British Columbia. It's actually worked quite well at reducing emissions. It's had very small impact on the economy. It's at $30 a ton. I mean, both the ETS and the California system, with cap and trade systems, have resulted in very low prices on carbon that are often just easier to pay than are really motivating people to act. So from our perspective, we really prefer a carbon tax, and we like it to be revenue neutral so that there aren't all kinds of perverse incentives for manipulating what are done with those resources.
So New Jersey did pull out of REGI, but it is still one of the more progressive states for solar. So if I buy a system for my house, which I did, the payoff time was 5 years. If my son who lives across the river in Pennsylvania put the same system in, his payoff time's over 10 years. So we have tax, basically credits. The governor had signed, again, to renew this program, SRECs. And so basically they put a price for the solar, and if for every 1,000 kilowatts you produce in your system, you get one SREX, which is traded on the market and it varies in price. It's been as high as 600, as low as 100, but it's been stabilized by the governor at around in the mid-200s. And so this is what makes the payoff time on, let's say, a $50,000 system go into 5 years. And I'd encourage anybody who owns their own house here to look into whether or not it's suitable for you. But I would also, 2 points I think I want to reemphasize is, one is that in order to do this nationally, we have to have a price on carbon. I think we would all agree with that. And otherwise, we have this insanity that if I move to Pennsylvania, it doesn't pay for me to put in solar power.
And I guess the last note to highlight on that is that that little footnote of owning your own home means that we have to recognize that this is not progressive, right? Home ownership is is something that the more affluent you are, the more likely you are to be in a home, and policies that exclude low-income individuals, like in California, rightly ran into a big hurdle. So our first climate law, Assembly Bill 32, did not have a big environmental justice element in it, and it was a big effort to get just as across the finish line. So there wasn't a lot of attention there. The new climate law, Senate Bill 32, that now goes to 2030 or further, actually demands that a very large part of the carbon revenues get spent in environmental justice needy areas. So for us, that's Central Valley, that's low-income communities. So finding ways to take these policies that initially, in their first version, were basically subsidies for the rich, subsidies for solar for people who already own homes, finding ways to do it. So right now there's a bill that has gone through in California. It's called Solar Gardens. And so as a renter or someone who is in a row home, you can effectively have ownership of a solar array on the rooftop of a neighborhood grocery store. So you're getting the benefits, but you don't necessarily need to be a homeowner. This is sort of in response to your question in the back, in the Rutgers t-shirt, because finding ways to make this a socially progressive process is got to be part of that long-term sustainable story, not just to make it better for those who already are kind of empowered.
Which is very consistent with the idea of a revenue-neutral carbon tax, equally puts money back in the hands of every individual, regardless of wealth and so forth.
I'd like to call an end to this. Our speakers will be here during lunch, but I'd like to just thank the panelists now very much. Thank you very, very much.